But let's continue with our second speaker, Professor Jaan Raik from Talinn Technical University. He will talk about the safety certification of AI hardware accelerators in the automotive domain. The floor is yours.
Thank you, Albert. And thank you, Ali Serdar, because you made my job a lot easier. So my challenge was that when I got the invitation from Albert to present in this workshop, I had doubts at how this thing is really related to automotive powertrains and maintenance. But actually, during the previous presentation, Ali Serdar already mentioned a lot of connection points. And so, first of all, so I'm just going to present what we do here in this lab, or what my group does or has done recently. And basically, we are concentrating on hardware implementations of AI, so sort of AI accelerators in hardware, and how to make these things cost-effective, resilient, and reliable. And then safety certification for automotive is one of the tasks where we are looking into in the standardization committees and with companies. So let me go through this topic. So basically, in automotive, there are threats of this AI or deep learning deployment. So basically, different kind of threats, actually. Some of them are like malicious. So there are some attackers who may want to do something malicious to our car. And so this is a security threat, but there are also accidental things like because we are talking about physical hardware, there are things that just fail and wear out and or are affected by temperature or radiation. And these things, they affect the way how our AI in the cars is working. So in this case, there is an object detection which actually misses the pedestrians in this image, and is misclassifying them as either not detecting them at all or misclassifying one of them as a bird. So there's clearly a safety problem here. And you know, over the times, there has been different obstructive concerns because of safety. Like long back in history, there was this Red Flag Act where it was required that the person walks in front of a car with a red flag, so that the horses don't get scared about car approaching. So and this act actually was in force for something like 30 years. And nowadays we have other actually acts that are regulating or that are going to regulate our automotive system. So we have a Act in the making, but there is also standards. One of them is like ISO FAS 8800, which is about automotive safety, and it's AI safety in automotive. And basically, a part of this standard is dealing with random hardware faults in AI systems. So basically, this is a new thing, and this is something that soon the car manufacturers have to take into account and have to conform with. But there are several there are several challenges here. First of all, like AI systems are different from classical computing systems. So there's a sort of probabilistic nature of them. There's also the explainability issues, as Ali Serdar mentioned. And so basically, the question for the engineer or for the companies there is that how actually they even measure the reliability. So there are fault injection tools and some classical methods, but they are not really very scalable. So the size of AI and these machine learning systems that are deployed is skyrocketing. And even Ali Serdar was showing these embedded solutions like TinyML and so on. But even the size of these is skyrocketing very fast. So this measurement itself is not scaling very well. And then the other question is like, well, if we can measure and we get the results, so how we are able to improve it without really doing too much without too high costs. And so in this regard, we have a kind of two kinds of research threads. One is we develop scalable tools for reliability measurement of AI systems. And the other thing is to find cost-effective ways to improve the reliability of AI systems. This is my phone. Can anybody switch it off? It's in the blue bag, sorry. Okay, so the talk is about, so I mentioned the ISO 8800 standard. I unfortunately don't have very much time to cover this, so I will jump into the research topics that we have been dealing with. So one is the reliability assessment. So I would like to present the deep figure approach that is jointly developed by Professor Maxim Yanichin, Professor Masoud Tanestalab, me, and our early stage researcher Mostaba Ahmadilivani. And so basically an interesting feature about this will be that it's actually matching somewhat to what Ali Serdar was mentioning about the heat maps of neural networks. So you can really build a heat map with this one. And then it also tackles the scalability issues, and of course, it tackles the robustness issue. And then on the other part of my presentation is then about improving the reliability once you have actually identified where the vulnerabilities are. So I'm going to talk about two of the works that we did. One is about the neuron splitting and channel splitting approach, and the other one is about activation clipping plus some training approach, and how they improve the reliability and what is the cost, what is the related cost. And finally, I'm going to say a few words about our other activities in the computer systems. And there's some time for question and answers, I hope. So first, the scalable and accurate assessment. So the first idea is a deep figure. So this is a resilience analysis, which basically operates in a nutshell like this. So let's say we have here a simple network, and so this is like for simplicity, this is just MLP, but it can also be another kind of neural network. It's actually not the principle. And let's assume that we have at some point in this network we have a fault, and we mark this fault by delta. So then what we do is we propagate this delta throughout this network to the output neurons, which are basically the classes, and we get an aggregated formula for the delta, which is then basically boils down to an equation where we can say that okay, this is the big delta 1 and big delta 2. So we calculate their values, and we get the condition, like if the condition for misclassification, and we say that if this delta is less than minus 5.39, we will get a misclassification. And we find these ranges for different data sets and different neurons. So there is actually it's a very exhaustive analysis, but there are ways how to make it really how to make this search really scalable. So we have papers about it which we can share later. But in the essence, what we get in the end is we get sort of ranges for each neuron or each element in the neural network, which say about the value ranges, like which of the value ranges will definitely lead to misclassification and which of the value ranges are safe. So we can actually have a sort of heat map for all the parameters or neurons or channels in the network, showing like, okay, maybe these neurons are all green, so they don't influence the faults there don't influence the classification, and we can see that some of the neurons are really highly critical, and so they don't have room for an error. And based on that, we also calculate several vulnerability metrics for the network itself. And so with this method, we have actually found we have compared it to the fault injection. So to sum up, basically it improves the scalability a lot. So we have here something that takes half a month by fault injection will run in this algorithm in half an hour. So it's a huge speed up, and it is the classification is also quite accurate. So it's near 100%. So more than 99.95% accuracy in this estimation of our classification of these critical and non-critical faults. So so this is kind of a core method that we are using for both the resilience analysis, but also later in the pruning and reliability improvement phases. So okay, so moving to reliability improvement. So there are a couple of cost-effective reliability improvement methods that we have developed for the neural networks. So one of them is a work that we did for quantized neural networks. So this is about actually duplicating the neurons. So basically, there are actually several works on actually replicating neurons to achieve fault tolerance. But what we did here is something really lightweight. So what we did, we used this vulnerability analysis to find out the most vulnerable neurons, and we duplicated them instead of having triple modular redundancy for these vulnerable neurons. And instead of voting, we were using just ANDing the outputs of these two neurons. And basically, here are the experimental results for this method. So what we can see is that regarding the accuracy loss, so basically here we talk about accuracy loss, so the less the better. So we can see that this red line and blue line, they are nearly identical. So these represent the triple modular redundancy and our splitting method. So we see that we get the same protection as with DMR, more or less, also for different networks. And then this black line, which is a straight line here, this represents the unprotected network. So we can see that an unprotected network is actually having a very large accuracy loss, which is like nearly constant here. But then with the protection approaches, we can actually limit it to a very low accuracy loss, even with a lot of very very vulnerable neurons. And then what is interesting is that okay, this is actually obvious, is that the overhead that we pay for the duplication and duplication, so the overhead is twice less. And it's also then also you can find a trade-off between the amount of protection and the amount of overhead. So what we can also see is that you can get fairly high protection with a really low overheads. And this doesn't require any retraining of your network. So this is just a post-processing step for your whatever network structure you happen to already have and whatever you have optimized. Then the other thing is to move from neurons to channels. So we are talking about CNNs, and we are talking about all these convolutional filters. And now instead of targeting and splitting the neurons, we are actually splitting channels. We're duplicating channels or duplicating the filters. So here are like different cases. Here are like different cases for checking and correction. And basically in the end you have the corrected filter and then some of the filters you don't protect because you can actually measure the vulnerability of it. So you're only protecting the most vulnerable channels. And in this approach, this is again a post-processing approach, so you don't need to retrain anything. You just have your CNN, and you just duplicate some of the filters that you have. And here we can see, here we can apply then pruning to channels, so we can actually prune some of these channels as a post-processing step. And what we can see is that we can get even better results with the pruned networks than with the unpruned ones. So they are even with even less accuracy drop. Whereas the hardware overhead is for the fully protected or fully TMR plus voter is really high. So we are talking about like 155%. We're talking about 200% overhead. Then with the duplication, it is smaller. But then when we use the filter duplication and actually pruning, we can get nearly to zero, or in some cases we can even improve the size of the network. We can reduce it while we increase the protection. So this works. This work has not been published yet. I think this has been submitted, but the previous works were actually published, and the links are in these slides. Then another alternative approach is that we are developing together with researchers from Talinn University, and this is about using activation clipping with progressive training steps to find the optimal threshold. So this is kind of like a student-teacher based method, which actually retrains the network to obtain the optimal clipping levels for the activation function. And so basically, oh, sorry. Yeah, so I don't have the results here, but basically this, in general, this activation clipping is a very powerful method in terms of, it turned out a very powerful method in terms of improving reliability. And there are works out there, but this method actually is giving even a higher level of reliability than the state of the art. So this is under review at the current moment, but this is rather complicated. I don't want to go into details, just want to mention alternative approaches. So one way is to duplicate the resources to either they are neurons or channels or parameters, and the other one is then to actually work on the clipping functions itself and make them more fault tolerant or optimal. And so there are also links from this to automotive security. So basically, the vulnerability ranges that we were looking at, they could potentially be used in some sort of monitoring of some malicious activity. So basically, we know the exact borders where things are going to become critical, and we also know the safe ranges. So we can see if some activity is like deterministically trying to go out of these ranges. So we can kind of do some image, and not image, but signal processing to understand like where the data is with respect to these ranges, and then raise a flag when we see some suspicious activity. So this somewhat matches to adversarial attack scenarios. And then we, of course, the reliability improvement techniques that were mentioned could be used in increasing the overall robustness against attacks. And this is something we are trying to find out in the future research. And then last but not least, mentioned by Ali Serdar, all this explainability, all this heat mapping could be done with such kind of vulnerability analysis. So we can actually make a color map of the network and show So where what depends on, or which are the most let's say significant neurons or significant parts of this network? So basically, it could be combined with explainability as well. And then there are other works that I unfortunately don't have time to present, but luckily Levent is here, so he's going to speak about the hardware security side that he's doing in his with his people. And also we have an adjunct professor, Samuel Ballerini, who is actually now a professor at CMU, so Carnegie Mellon University. He's actually visiting us this week. So this is a hardware security topic that will be mentioned. There is also Professor Tara Kasempouri's group. They are doing security verification, security property mining mainly, and they have several applications in automotive, actually in self-driving cars. So they have been working with this Taltek Siseauto self-driving car, and they have actually a paper about it at this year's state conference. They had it in April, so it's pretty good quality as well. And then last but not least, our colleague, Professor Maxim Yanichin, and also in his group, Dr. Artur Jutman. What they do is different things. So they basically, Maxim is coordinating Horizon Europe Marie Curie training network, Tiramisu, and also a twinning project called TIChip. So this is AI chip, and T stands for Taltek. So these projects, they are also about open source, like RISC-V, let's say hardware open source technology libraries, open source EDA tools. So again, some overlapping points with what Ali Serdar was mentioning. And also regarding these AI accelerators, what Maxim with his students and also our group has been joined there. What we have been doing is about approximation for AI accelerators to increase the reliability. So it's sort of approximation reliability trade-offs. And also in Maxim's group, so Artur Jutman, who also is leading a technology company called ESTONIA, which is actually situated in this building. What they do is also some works on system health checks for computer systems, like online fault management, health mapping, and such kind of things. And so they have been participating also in many Horizon projects with these topics. So I find it kind of related to what Alper and Ali were presenting today. So this is in a nutshell about our group. And thanks
yeah, thank you very much, Jaan. Is there any question about Jaan's presentation?
I can ask. Thanks, Jaan, for complimenting. I'm just really. It makes me really, wonder how pruning also improves the reliability. Not only improves the energy efficiency, but like it, as you said, I think getting rid of the overfitting, getting rid of the things, the unnecessary. It can also improve the reliability. I mean, it's great, really.
Unfortunately.
Hello?
Can you hear me?
Can you hear us?
Yes, I can hear you. Did you hear my question?
Ali?
Hello?
This link is over now. It happened again,
Okay.
No, we can perfectly hear you.
Okay.
I don't know. Maybe
We can hear you well, no problem, Alper. Can you hear me?
Can you hear us, by the way? Hello?
Yes.
Yes. Now we can
Okay.
hear you.
Okay, so there was some technical issue, so we dropped out for the second time. But I think I got Ali Serdar's question. So the question was about how can the reliability be improved if we actually prune the network, if the network becomes smaller. Yes, so
Yes.
so Mojtaba in the audience. So can you tell me what is happening? So
yeah, one of the facts is that
louder. Yeah.
one of the facts is that the size of the neural network is actually reducing, so we will have a smaller footprint on the device.
Oh yeah.
But
So, yeah.
the other thing is like we are basically using pruning for reducing the cost rather than improving the reliability. So there are these twofold views of this exploitation of pruning here.
Yeah, but the question was about how reliability increases. Yeah, so one of the aspects that the Mojtaba here in the audience points out is that the footprint of the network becomes smaller. So there is like less things to be affected in the whole network.
Yeah. I understood, but it was very great thing. I never thought about it that way. So thanks for the eye-opening, showing us this. Yeah.
Actually, one more comment on that. Actually, we are not the first one to observe this. But what was really interesting about Mojtaba's work was that we used a very different kind of pruning, or let's say the vulnerability ranking from the classical one. And we found that with this other pruning method, or let's say not the pruning method, but the other method, how to actually find out what is vulnerable and what to prune, how to rank these neurons. With that, we could actually get to much more optimal and much more reliable neurons, because there were methods which were actually pruning based on vulnerability, and they said, okay, sometimes we get a better reliability, but in fact, we could also propose a much more adequate ranking, or let's say the vulnerability estimation method, which then increased the reliability even more. So we can actually show these two pruning methods in our ranking pruning methods in comparison, and it's also important based on what you prune, and this difference is significant.
Thank you. Yep. Thank you.
In the meantime, Jaan is very active in the standardization activities. I will also come to this in the brainstorming session because we may need some more time to discuss this topic because it's very important. But before proceeding to the third presentation, I have a small question because it was really impressive, the deep vigor algorithm. So it reduces the 2-week duration to the minutes, from weeks to minutes. Is there any reflection in the industry? I mean, do you have any contacts with the automotive industry or some other industry?
Actually, when Mojtaba first presented it, we immediately caught the eye of ARM. So ARM is very interested. So their functional safety unit is really interested of this. And actually, so they are also moving towards that direction. So they have been looking towards that direction. So we have been working with them for a while. And also we have been discussing with people who are not in this, like also outside of automotive and outside of this embedded and edge AI. So basically, when we look at data centers, they also have this silent data corruption problems, and they are still running the AI algorithms there, like Meta and Google and these companies. So they are also interested of how we can, somehow assess and protect these kind of algorithms running in a scalable way, because their models are huge.
Yes. So I see a big potential. Wish you the best luck for the technology transfer to the industry.